Hello, welcome. Glad you could join us for another Tech Talk. Again, in our studio, Bruno Putzeys. Bruno, welcome again.
Thank you for having me.
Yeah. Today, ladies and gentlemen, we'll be talking about the Purify drivers. Interesting topic, Bruno. Let's kick off with before there was actually a driver made, you had to improve measurement systems. Tell me all about that.
Yes, the thing which we wanted to do, as you recall, is we wanted to try and identify the dominant remaining distortion mechanisms in loudspeaker drivers, and the way to do that was actually to try and work out a simulation model for what was going on inside a driver. Now, by simulation model, I don't mean sort of a magnetic simulation like everyone would use an FEMM or FEAR type simulation. You can use those to predict what a driver will do, but what that simulation will not tell you is why. So to get an understanding, like how precisely does certain behavior relate to the geometry of the driver and the disposition of the magnets inside the system, for instance, you actually need a kind of I would say a simplified model, but that does accurately capture what the driver will do. And so I think we spent almost 2 years just talking about the motor model. That is to say, the motor of the driver. So is a driver. I'm sorry to my colleagues, it's an old one, so it doesn't have the nice red painted plate, but it's one of our drivers. So the motor is everything magnetic plus the voice coil. That's the motor of the driver. Okay. And I think the best part of 2 years to have a what we say a physics related model, but one that was quite simple in terms of number of calculations, or even how he would represent it on a piece of paper, like how he would explain how it works, and that model actually successfully predicts virtually all distortion mechanisms that you find in a motor, with one notable exception, which is the magnetic hysteresis distortion, which I also touched upon in our talk about the amplifiers and the output choke, and that model then subsequently told us, okay, well, clearly these things are the items that need to be that we need to find a solution to. The biggest one was an effect, I think I mentioned it a while ago, which we call the Cunningham effect, which is the fact that if you have we've got a voice coil, which is partly sitting inside a magnetic circuit. I'm sorry, I would love to have a cutaway model, but I haven't. So you have to use your imagination. So anyway, so there's part of the voice coil which is actually sitting inside this this magnet. That part of the voice coil, well, the whole voice coil actually produces a magnetic field as you pass current through it. And the one biggest problem is that part of that field will actually end up being added to the field which is created by the magnet. So meaning that if you pass current through the voice coil in one direction, the field strength in the air gap will increase, and if you pass current in the other direction, the field strength will decrease. And until recently, people thought that effect was distinct from another one, which is called reluctance force, which is that if you imagine there not being a magnet, but only the iron parts, that if you pass a current through the voice coil, then the voice coil will basically attract the iron, and irrespective of the direction of current, the voice coil will be attracted inwards by the iron, which until recently was thought to be distinct from the fact that if you push the cone in, and the entirety of the voice coil sits inside the magnet system, in a normal driver, the self-inductance of the voice coil will actually increase and will be it will reduce when you push the driver out. The big breakthrough that Lars made. I remember the day like yesterday that he said, "Well, bloody hell, these aren't three different effects. They are not simply related. They are the exact same thing. There is nothing to differentiate one from the other. They are simply different ways of how the same effect manifests itself, and that then subsequently allowed us to put that into the model exactly. So we've published a paper about that, which is also available on the website. There is one tiny bit of the recipe missing, which I shan't mention because it isn't mentioned in the paper either. But basically, what this is about is actually explained in that paper. Once you're able to model this, it also means that you can actually train that model to emulate any loudspeaker driver. And this is sort of the point where we sort of got off got off the train towards the speaker distortion compensating algorithm, and decided to do our own drivers, because it became perfectly clear that there were a couple of small things which you could do to eliminate that problem, and as a result keep the driver inductance completely constant over an enormously large range of excursion. That's when we said, okay, we're gonna do drivers, and that's when we built it. This model also informed how we measure speakers. So we have a system which we simply call the red box, or in Danish the lower box. That's simply basically a slightly oversized sound card with a big amplifier in it, and highly calibrated, that can probe a driver by putting in a large signal and then seeing how it moves and what the resulting voltage is, and then from that it can actually deduce the actual all the important parameters of the driver, actually including stiffness of the suspension and everything. So that's actually been wildly useful to us, because it is so fast and it's so accurate. But in the end, what we do find is that if we do a magnetic simulation, so one of these finite element things, or we run our model based on information gleaned from a measurement, the results match up exactly. So it's kind of a golden thread that runs through the whole Purify development, is that we always like to be able to model, i.e. calculate in sort of a more or less human readable form in the formulae and circuits and equivalent circuits and whatnot. We also like to be able to simulate, and then we like to be able to measure, and all three have to match up. If that chain breaks anywhere, then it means that we're in the dark, or at least that we're in the dark as much as anyone else is.
But let's get back to the measurements. As I understand it correctly, you guys are able to measure beyond the scope of any other loudspeaker manufacturer today. So meaning that you can measure things that weren't measurable, let us call it that for the simplest things.
Well, it's not so much to do with being able to measure things which are too small to measure, but simply things where people didn't know how to separate the different elements out of the signal. Okay. So you would have you put a signal through a loudspeaker, and a loudspeaker, you cannot measure a loudspeaker with a single sine wave. Of course, one does because people are are habituated to reading plots with the frequency response overlaid with harmonic distortion and so on. But that actually hides an enormous amount of information. So you need you need to apply a much more complicated signal to a loudspeaker. But as soon as you do that, of course, you get a fantastically rich intermodulation distortion spectrum, and how are you going to unpick that? And it is precisely being able to unpick that complicated spectrum, and actually being able to point at the different elements in the construction being responsible for what precisely in that measurement, that allows us to validate drivers to such an extent. And the easiest way to look at that is to just open up one of our driver data sheets. What you find is that I mean, we are already sort of more detailed than most people in simply including the variability of, say, the BL product with excursion. But we go far beyond that because some people are now also stating these in their data sheets. Not many, but some. But we have inductance versus position at any frequency. So we've got graphs with a family of parallel curves showing well, at this position and that frequency you get that inductance. And those are things which people might have been able to simulate in the past, but we're the only ones who actually know how to measure them. So of course we are teasing our competitors a bit by saying, well, everyone should have this data in their data sheet, so of course everyone should. But we're the only ones who can, because we've figured out how to actually get at this data from an actual physical unit and not a simulation.
So with the help of that data, you were able to point out the things that needed improvement in the designs. Yeah. And can you elaborate on those improvements? So there are some that are very obvious.
Yeah, so the let's say the big improvement on the motor side is there is a cutaway diagram floating on our website somewhere, showing that the central part. So a normal drive has sort of this dish with a cylinder sticking out, which is called a T-yoke, because we're looking at it from it's a T. So we replace part of that T-yoke by a permanent magnet, and that's actually not to strengthen the magnets on the outside. It's actually a way of conducting the DC field to the air gap without actually adding magnetically permeable material. We sometimes jokingly call a magnet saturated air. That is to say, the permeability of a magnetized magnet is 1. And as a result, you know exactly how much flux will go through it. No matter what magnetic field you apply externally, and that dramatically reduces the inductance of the voice coil to such a degree that it already becomes virtually independent of the position. And then there's a piece hidden on top of the top plate, which is a tiny bit of iron, very precisely shaped, which actually slightly increases inductance, but only when the driver moves outwards, so that we can actually sort of balance that tilt out, so that the inductance remains constant over a large stroke. And another way of looking at it, as I said, it is exactly the same thing as saying that the voice coil is being attracted to the iron, is that either when it moves inwards, it might be attracted to the pole plate, and when it moves out, it will be attracted by this little thing we've got on top. It's another way of looking at the same thing. So, having done that, and also famously, I don't think the cameras can easily show that. That the voice coil is not uniformly wound. So there's some turns missing, so it looks kind of ugly. That actually helps make the force factor even more constant over the range. And at that point, the distortion of this motor is extremely low, so we were really, really looking forward to them building a driver with this motor and listening to it and measuring it. And that's when we ran into this massive disappointment, which was that the harmonic distortion, simple harmonic distortion, hadn't budged at all. Well, it had budged, but barely. So I still recall sort of doing a back of the envelope calculation after. Lars was really distraught at that point. He said, "Well, what are we doing this for?" And he was trying to prove that the motor had a problem, and he could only find with ever cleverer measurements that the motor was functioning magnificently. And finally, I said, it's looking like it's the bloody surround that's causing the problem." And that actually turned out to be the case. So, in order to illustrate the point, this will go bang for a second. I've brought us a driver from someone else.
Okay.
To try and see if I can explain what's going on. So this is what we call a roll surround. So I'm going to give it push it out. So I've pushed it out, all the way out, plus a small movement. If you now look closely, then you can actually see that the cone is moving, but only really the cone, and the rest of the surround is almost stuck solid. The surround is not moving at all, right? So the radiating surface when the driver is sort of fully out is really only the cone area itself. Which and if I then do the reverse and I'm going to push on it, and actually drivers can handle quite a lot of pushing. The inverse happens. You can see that the whole surround follows the cone except for the outer edge. Yeah. So this means that the effective surface area now increases, and of course the effective surface area multiplies directly into the efficiency of the driver, meaning that the driver's mid-range response will drop if it moves forward and will increase if it moves back. Yeah. And that effect is this thing looks innocent, but this surround can be nearly 20% of the whole cone area, meaning that the efficiency of the driver will go up and down by more than a dB if it really starts moving, which causes amplitude modulation and second harmonic distortion. So the usual trick whereby people say, "Oh, the radiating surface will be just sort of halfway up the roll," that's incorrect because the effect, even at small excursions, that effect already takes place, and the solution we stumbled upon, well, let's say the half solution, and I mentioned a bit earlier that sort of the basic idea is rarely the clever one. Here's a case where the basic idea on the driver is say, okay, well, you just cut the surround up in a number of slices, and one bit goes up and the other bit goes down, one bit goes up, so that when the cone moves out, the radiating surface here decreases and it increases there, and so that balances out. And if you then start looking at literature, and then you will find that there are actually quite a number of publications out there of people having tried something like that, and for some reason you don't ever see those in the wild. Well, we quickly found out why. Because the thing is, if you have an ordinary nice half roll like that, and another nice half inverted roll there, and how do you segue from one of those regions into the other? Well, the simplest way of segueing is just like in a straight line, but that actually creates a straight piece of rubber that no longer bends but stretches. And you can also have sort of this W-shaped thing, which is a lot better, but is still not enough. So the clever thing was Lars saying, "Hang on, I need to put some stress relief on that thing," and so he added this wobbly little ridge. But what that does is it simply adds add some material, some relaxed material that gives you the extra give to be able to move easily without actually producing any tensile stress on the rubber. So the basic idea, which you would think of as the clever one, was actually the simple one, and the clever one is this little ridge, and because the drivers looks it kind of looks almost obscenely biological, so we call it wormy.
Okay. When you see this, you can immediately identify it as, this is a Purify driver.
Yeah, it is now working as a trademark, and what we found was that initially people went like, that doesn't look normal at all, but it went very quickly from looking abnormal to being a mark of quality, because it says, okay, well, this is recognizably a Purify driver.
Yeah. So this one is actually one of the first designs.
Yeah. So this is the old 6.5 inch paper cone. So basically, we carry two lines, a line with paper cones and a line with aluminium cones. Aluminium cones having a smoother response until a relatively violent breakup, and paper having a pretty smooth response. But breaking up inside the working band, which produces slightly different distortion profiles. Actually, I think in any other driver you would not be able to spot the distortion created by the cone in the measurement. But because our motors have such low distortion, you can actually see what the cone is doing when it flexes slightly. So the aluminium cones are a bit more challenging to work with crossover wise. So that's why we've got an app note in the explaining precisely how you have to deal with that breakup peak. Because it seems that most speaker designers deal with that breakup peak in the exact wrong way. Let's say, if you want to produce if you build a passive speaker and you want to create a suck out in a particular region, a notch, in this case to cancel the peak in the frequency response, you can either do that by taking an LC series network and strapping that in parallel to the driver, and then together with the impedance of your crossover filter, that'll notch it out. Or you can build a parallel LC circuit that you place in series with the rest of the crossover, which basically means that at this breakup frequency, the driver is essentially isolated from the rest of the world, and that second method turns out to be the best method, because even though we put a fantastic amount of effort in eliminating hysteresis distortion in our drivers, there is still a tiny little remnant there, which of course gets amplified by that cone peak. And if you then then actually present the loudspeaker with a very high input impedance or with a very high drive impedance at that frequency, then whatever that the iron core is doing at that frequency cannot produce current in the voice coil, and hence cannot produce force in the voice coil. So in one go, you get rid of the of that breakup peak, and you remove any harmonics associated with it that land at the same frequency. So if you follow that, then the aluminium cone drivers are definitely the ones that give you the best result.
Mm-hmm.
It's only if you really insist on making a simple crossover that we'd say, well, in that case, paper will be sort of a much friendlier partner for you.
So you talked about the motor, about the surround of the cone. Any more changes?
Actually, not that much. No, it's so. Otherwise, this thing looks like a fairly normal driver. So it is kind of funny to see that sort of the number of distortion sources that were still outstanding in speaker technology was not that large. I mean, so you get so you get the Cunningham force. You get the SD modulation, as we call it. So the SD is the radiating surface area, and then you've got some of that hysteresis distortion. And once you tackle those three, you basically have distortion more or less sorted, and then everything else, like optimizing the cone profile such that that any vibration or any resonance in the cone get dumped by the surround and that sort of thing. Those are really those are the kind of refinements that you would expect anyone to make. Not that necessarily everyone does, but some do. And because in the end, of course, if your super low distortion drive does not have an easy frequency response to work with, then people still won't want to use it. So. But that's let's say that part while it clearly appears to be enormous fun to do. I mean, looking at Lars, it is par for the course for driver design. But the fundamentals are these measures that we take to reduce distortion.
Yeah. Is there a particular reason that you guys started with designing mid-range, mid-bass units?
Purely because that would be the thing that would be easiest to launch into the market, because you know that two-way speakers are quite a popular format, and within that format, speakers with a 6.5-inch driver is kind of the dominant size. So this was really purely a practical choice, saying well this seems to be the type of driver that would be easiest to sell. And then we'd work our way down and up from there.
Yep.
So currently the lineup starts at 4-inch and ends currently at 10-inch, which is an absolute monster.
We're talking about the 4-inch, Bruno. I remember having a first listen to your the little Speak.
It's called the Speak 8, yeah.
The Speak 8 with the 4-inch active and the two passive. The amount of bass that it can produce, it's extremely. How do you achieve that?
Keep in mind they are long stroke drivers, so they can move a lot of air. But the important thing that they can do is that if you look at the kind of distortion that you get when you overdrive a speaker, then say if you have the kind of distortion that happens when you sort of really push the suspension up to its limits, when it won't go much further. Actually, at that point, the suspension still moves more than enough to pass mid-range frequencies untouched. So if this is the only distortion mechanism that you've got left, which is actually the case with purified drivers, the only dominant distortion mechanism that we don't touch is simply the fact that the suspension is progressive. It stiffens up as you move out, and you do that because you don't want the driver to what they call hard bottom. You don't want the voice coil actually to hit the backplate, because if it does that produces an almighty bang, and is not nice to listen to at all. So you do want the suspension to gently stiffen up as a driver moves. But if meanwhile the motor itself remains distortion free at that point, then you only end up with pure bass low frequency distortion. Whereas with any other driver where either the voice coil current or the cone position changes the amount of flux that's seen by the voice coil, then you also get amplitude modulation from the bass into the mid-range. and so there is so if you go on our blog, you'll find an article with a couple of sound samples. So I've prepared a simulation where of sort of two drivers. One driver that is normally perfectly linear motor-wise, but has a very non-linear suspension. The other, which has a perfectly linear suspension, but is non-linear in the motor. I've tweaked those two simulated drivers such that if you measure them with a pure sine wave and you sweep the sine wave and you look at the harmonics and how they change with frequency and amplitude, then those two drivers look almost identical. So the armchair psychoacoustician would say, oh, these two drivers are going to sound the same. Then we run music through them. And you can listen to the processed samples and to the original. But what you then find is that the distortion that's caused by the suspension stiffening up is virtually inaudible. It is audible if it gets really, really bad, but it's not really terrible at all. Whereas if the mid-range starts being amplitude modulated by the position, it sounds burbling. So one of the reasons why you can get such a ridiculous amount of bass out of the Speak 8s is because when you are doing so, you are actually overdriving, and they are distorting, but they are distorting in a manner which is very hard to hear, and if you can hear it, not particularly annoying. So that's it. And so for us, that little speaker is kind of what we use to illustrate to people how what our technology can do. Because if we wanted to do the same thing with a two-way system with an 8-inch driver, we would have to play so insanely loud that there's probably people's ears that would start distorting at that point, not the speaker. So the 4-inch system, the Speak 8, is just a lovely little system. Well, it is a lovely little system, period. But it is fantastic for demonstrating that. And it's kind of a message that I'm trying to get out to people is that I told when we were having coffee a while ago that I see almost 3 different tribes in the audio world. So you have some people who will simply say a certain percentage of distortion is no longer audible, and those are very often people who would label themselves as scientific. Then you have certain people who would say, oh, measured distortion doesn't matter, but fabulous impacts of cables that does matter. And then you've got a third tribe that says, no, you absolutely have to push distortion down, at every type of distortion down as much as you possibly can. And I would say that those 3 tribes are wrong, all 3 of them, because there are types of distortion which you actually cannot hear. There are types of distortion which you can hear, but which are not particularly annoying to hear, so which don't really get in the way. And then there are types of distortion which are both audible and very nasty. And if you want to get anywhere in this line of work, you have to know which kind of distortion you are dealing with and where they sit on that scale, and then you can make choices. And so simply choosing to design a driver such that its only remaining distortion mechanism is that stiffening suspension that leaves you with a driver which you can easily overdrive, which is tremendously robust. The power handling specifications on these babies is ridiculous. I mean, this thing has an AES rating of 400 watts, meaning you blast it with 400 watts of a particular kind of peak noise for 100 hours, and then you take it off the test bed and you remeasure the specs, and they are not allowed to have changed by more than a certain percentage, and there may not be any visible signs of stress on the drivers. This is for a 6.5-inch. This is astronomical, and that's down to a whole lot of parameters in production, a whole lot of parameters of choices of material, and the fact that we that we actually choose to let the suspension correctly control excursion. So this is apart from this is not just a driver for idealists. This is actually a very practical thing.
So we've been making drivers for decades, but now finally we can make drivers with distortion that is way down there. But what does this actually mean for our listening experience?
There's actually the parallels with amplifiers are in a way quite striking. But with speakers, the thing which you especially want to would like to listen to, then or that they should pay attention to, is very complicated sound stages. So the kind of what we call plinkety-plonk audiophile demo music, that type of music is almost designed not to challenge any loudspeaker. So what you should actually do is you should play full orchestral music, or very complicated. I mean, even rock and pop is all fine because it's stuffed full of information, and if that information is there and you can pick out the stereo image and you can hear whatever either was actually happening in a concert hall if it's an acoustical recording, or what's been done in the production and how the whole thing is put together. If you can hear that, and you can hear that at a quiet volume, and you can also hear it at a very loud volume, that's the sort of those are the hallmarks of a low distortion loudspeaker.
Yeah, I've had the privilege of listening to a lot of designs or implementations yet, and I find it indeed true what you say, and also that it's the experience becomes more real. It's you can almost, how do I say it, taste the music. You become a part of a part of the process instead of sitting there and watching a nice representation. So it's emotionally more compelling. Yeah. And that's quite interesting, I must say.
Yeah, and so this is where at any point in what I want to do, what Lars want to do, what all my colleagues want to do, is we want to find the part where being hard-nosed engineers actually results in musical enjoyment.
Yeah. Well, this has been quite an interesting tech talk, Bruno. Thank you for sharing all this information about the Purify driver designs and the insight in the technology. Well, wow, quite interesting. Yeah. So viewers, that's it for this tech talk. We thank Bruno for sharing all about the Purify drivers. Thank you for watching. See you at the next one.